Today we're talking about different types of solids. Solids can be arranged in a number of different ways. They can be crystalline or they can be amorphous. Here's just a few types of crystalline solids that can exist. We have cubic body centered here. We have cubic face centered and hexagonal. And you can see some regular atoms, elements from the periodic table that would fall under those categories. So that means that at every one of these dots would be an atom of, for instance, iron. Iron, if you could get to the very smallest level of iron, you would see that the atoms of iron line up in this pattern. They make a crystal lattice pattern. And it depends on the element as far as what type of pattern they will make. This is true of all crystalline solids, not just the elements. So anything that is held together by ionic forces, by metallic bonds, or ionic bonds, metallic bonds, or covalent bonds, or by intermolecular forces, all of those solids that are crystalline have some sort of repeating pattern to them. You can't predict what it's going to be, but they'd all have some sort of pattern. Here are a few of those in a little more detail so you can see in three dimensions. It would be a simple cubic crystal. Sodium chloride, an example like this. So in that case, we'd have ions at every corner. So this would be a sodium, chlorine, and they would alternate. And every sphere could be a ion, molecule, or atom, depending on the type of solid we're talking about. This is an example of a cubic face-centered crystal. So each spot where you see a sphere here would be someplace where an atom could be, or a molecule, or an ion, depending on the type of substance we are talking about. So molecule, atom, or ion. Notice how we have a cube, and then on every face of the cube would be another atom, molecule, or ion. This is an example of a cubic body-centered. So if I rotate this, you can see that every sphere, again, would be an atom, molecule, or ion. Depending on the type of solid we're talking about, we have something at every corner. Plus, in the middle of the cube would be another atom, molecule, or ion. So this would be a repeating pattern throughout that crystal. All right, let's talk about each of the types of crystalline solids in a little bit more detail. First of all, we have metallic. Metallic would be any type of metal from the metal elements, so everything to the left of the stair-steppy line thing. And alloys. Alloys are just mixtures of different metals used for different types of purposes. For instance, in this case of the trombone, it would be brass. This is a gold-plated iPod shuffle, something everybody needs. Metals are all malleable, ductile. Malleable means you can put them into sheets, like aluminum foil. Ductile means you can draw them into wires. They conduct electricity because they have mobile electrons that can move through the metal, and they conduct heat also because of the electrons are mobile. Some examples: iron and gold and silver would be elements from the periodic table, and a couple alloys examples would be brass and steel. But really anything that is a metal in the periodic table, which is the majority of the periodic table, those elements, and then any alloy would be considered a metallic crystalline solid. Another type of crystalline solid is covalent network. So metallic solids are held together by metallic bonds, which we spoke about back in Chapter 6. Covalent network solids are held together by covalent bonds. So in the cases down here of diamond and graphite, both of them are held together by pure carbon, but held together by covalent bonds a little bit differently. So the graphite pencil that you have, what it is we have these layer of carbon atoms, and then they're held together by these weaker bonds. Each layer is. So when you write with your pencil, these layers are coming off. Whereas a diamond are held together by all strong carbon bonds, or covalent bonds between the carbons, which is a very strong setup. That's why diamonds are the hardest substances in the world. So they're bonded covalently. They're hard and brittle. They have very high melting points because of these strong covalent bonds. And just a couple examples be diamond, graphite, and quartz is also an example of this. So metallic metals or metallic solids held together by metallic bonds. Covalent solids held together by, or covalent network held together by covalent bonds. Next type we're going to talk about is ionic. Guess what? They're held together by ionic bonds, which are just positive and negative ions next to each other, and a bond is formed from the positive and negative attraction. So ionic bond, they're arranged in a pattern, just like all of these are. They're crystalline, they're all arranged in a pattern, but in this case, those corners of the cube, for instance, would be ions. In the case of metallic metal solids, those corners or the parts of the crystal would be atoms. And in the case of covalent network, they could be atoms or they could be molecules. In the case of quartz, it'd be a molecule at each of those corners of a sphere, for instance. They're hard and brittle, they have very high melting points, and they're good insulators. The reason why they're good insulators is because these ions aren't mobile. Ions have to be able to move to be a good conductor of electricity. Since those ions in the solid aren't mobile, they're rigid in fixed positions, they are good insulators. And these are tough to break, these bonds, so that's why they have good high melting points. Just some examples, but it could be any metal, non-metal, just some examples of ionic substances. So all three of those are considered crystalline solids. All of them are held together by pretty strong bonds, ionic, covalent, and metallic. Those three are held together by stronger bonds than the next one, which is called covalent molecular. Well, how are these different? Well, these are molecules not held together by covalent bonds or ionic or metallic, but they are held together by intermolecular forces, also known as van der Waals forces. So they're held together by intermolecular forces. And remember, these forces are quite weak compared to covalent, ionic, or metallic. They are about 100 times weaker. And because of that, these solids don't typically stay solids very long. So for some examples, they have low melting points and they're easily vaporized because these forces are not as strong. Ice is an example. Well, when it's cold out, ice stays ice, but in normal room temperatures, it changes to a liquid. Dry ice goes from a solid to a gas. Solid nitrogen would quickly change to a liquid and then to a gas because of these weak forces that hold them together. So, what would be at the corners or the parts of that sphere, those models that I showed you? In this case, it would have to be molecules because molecules are held together by these forces. There's also a possibility of those being noble gases. So that in that case, it would be atoms. So for instance, if we had solid argon, the points of the crystal would be argon atoms. So it is possible to be an atom or a molecule with covalent molecular. Last type of solid I want to talk about is the amorphous solids. What's different about amorphous is that there is no pattern to them like the crystalline solids. Their arrangement's very similar to liquids, and some people think that they're so similar to liquids because there is no pattern to them, because they are random, that they are just a very, very viscous liquid. They just can't move around each other nearly as much because as a regular liquid, they're not fluid, but they're just a really, really thick liquid. That's what some people think because of the arrangement. But everything that we know, everything that we see glass, we see ceramic, we know these things as solids, but just the arrangement at the atomic level is not the same as other types of solids. There is no melting points, however. If we would melt ice, we would see that at its melting point, it would stay the same temperature for a while. Amorphous solids do not have a certain melting point. They just get softer and softer, and then all of a sudden they would turn into a liquid. Some examples of amorphous solids would be glass, plastic, and ceramic. Rubber would also be an example. But amorphous solids, no pattern. That's the important thing. And there's just no crystalline structure like all the crystalline solids have. Thank you.